Welcome to the reactor hall of the Budapest Research Reactor, which is the most significant research infrastructure in Hungary, and it is the neutron service provider of Szeri-Kerék. Large-scale facilities are high-tech tools to advance material science, engineering, and technology. Here we use neutrons to study the composition and macroscale atomic structure of the materials in a non-destructive way. Neutrons are produced in the 10 MW research reactor and propagated to these experimental stations in so-called neutron guides. I'm Margit Fabian, and in this video I'm going to show you the neutron diffraction activities at the Budapest Neutron Center. Neutron powder diffraction is a standard technique for studying atomic and magnetic structures. The PSD diffractometer is placed on a tangential thermal neutron beam of medium flux research reactor source. The diffractometer is suitable for structural studies of solids, liquids, like amorphous materials in the range of momentum transfer up to 10 inverse angstrom. The wavelength selected from the primary neutron spectrum is 1.068 angstrom, for which, in the case of copper 111 monochromator single crystal, a neutron flux density of about 10 to 6 neutron per square centimeter per second can be achieved at the sample position. Scattered neutrons are detected by position-sensitive detectors. We have 3 helium detector tubes, which span a scattering angle range at 25 degrees. The cover of whole scattering angle range up to 110 degrees data are collected at 5 distinct positions of the detector system. The resolution that can be routinely achieved by such a setup about is 10 to -2 in terms of delta D per D. Neutron diffraction is a non-routine complementary technique allowing detection of light elements, discrimination of neighboring elements and isotopes, investigation of magnetic structure. Substantial amounts of sample needs and incoherent scatterers must be avoided. How is hydrogen? Moreover, is a non-destructive method. The neutron diffraction technique can be used to measure different kinds of structure. In example, the structure of atom clusters and molecules in different kinds of disordered materials. Glasses, for instance, lack long-range order but may have medium-range ordering over several atomic lengths. The measured diffraction pattern is related to the position of atoms relative to each other in the glass. Usually, we measure powder samples and fill about 6-5 grams in 10-volt cylindrical vanadium sample holder. Measuring time depends on the composition, with special focus to the neutron scattering lengths and atomic concentration. The complete diffraction spectrum up to 110 degrees in 2 theta is collected by moving the detector arm in 5 steps. Neutron diffraction techniques are used to investigate crystalline solids, amorphous samples, liquids, and different kinds of engineering materials. We describe here a neutron diffractometer with position-sensitive detector system used for structural studies of amorphous materials. In contrast to crystalline materials, liquids and amorphous materials do not have long-range translation symmetry. Thanks to the available resolution, this instrument is dedicated to study the structure of amorphous materials. Materials can have varying degrees of disorder. Instead of having well-defined atomic position, one must refer to a distribution of atoms as a function of distance, how is to the probability of finding an atom at a distance r, provided there is another atom at the origin. The so-called pair distribution function is proportional to this probability, and this is the function that can be obtained from the diffraction experiment. A measurement of the neutron diffraction pattern from an amorphous solid involves determination of the scattered intensity as a function of the elastic scattering vector. In the experiment, the scattered neutron intensity is measured as a function of 2 theta, from which intensity function SFQ of scattering vector Q can easily be determined. For an amorphous solid, SFQ is a continuation function tending to infinite. The structure factors are related to the structure in real space through a Fourier transformation. This will be the partial structure factor. From the partial structure factor, we can calculate the partial atomic pair correlation functions. After that, the coordination number distributions. And, if we are lucky, the bond angle distributions. In general, neutron diffraction is the main tool to study the structure of amorphous, liquids and crystalline materials. Our diffractometer mostly is dedicated for amorphous structure. Example, the local structure of a borosilicate glass is investigated by using neutron diffraction methods on the PSD powder diffractometer. Applying the software package developed at the facility, we can get the main structural information for the borosilicate amorphous samples. We can determine the short and medium range order, and to do this from the neutron diffraction measurements, we need to obtain the atomic distances, coordination network, bond angle, and ring distribution of the main atoms. Depends on the composition, concentration. The measurement time can be 2 hours or 24 hours. We are happy with very fine powder samples, and we prefer to have minimum 3 grams for a reasonable measurement with appropriate statistics. The measured samples are rarely activated. If it happens, we can store them, and after they decay below a well-defined level, we can hand them again. Yes, if the protocol is followed, then it is a safe and effective measuring opportunity.